All right, so welcome back. We are now in lecture number 13, I believe, for Math 140 SCI. Last time, we worked or spoke about the idea of a confidence interval, which is one of the two major aspects of statistics, or at least the remainder of the course. You have confidence intervals, right? So you have right, last one was confidence intervals. So let's just recap quickly. The idea of a confidence interval is you don't know a parameter. You estimate parameter using a statistic, and your estimation is a range of values. Estimation is a range of values. And the formula that we used in our example was x bar minus z star sigma over the square root of n. This is an example to x bar plus z star sigma over the square root of n. All right, so that's the idea of a confidence interval. We did that last time. Are there any questions on what we did last time that you might want to ask about before we move on to the next major topic? Okay, then we're going to move on now to the next chapter, which is the next major idea. And this is hypothesis testing. And if you look on your calculator and you have that stats test, you'll see half of them are labeled as tests and half of them are labeled as intervals. So, right, the intervals are your confidence intervals, and the other half are your hypothesis testing situations. So this is now chapter 17. So this was chapter 16, and hypothesis testing is chapter 17. And once we have the ideas of confidence intervals and hypothesis testing down, then in the subsequent next 6 chapters or whatever it is, what we're going to do is we're going to look at other situations for other confidence intervals and hypothesis testing. For example, the confidence interval that we did so far was if you are looking for the mean and you know sigma, then these are the formulas that you use. Well, what if you don't know sigma? What if you're not looking for the mean, but rather you're looking for a proportion? What if you're comparing 2 samples? Then maybe you're looking for the difference of the means or the difference of proportions, whether you know sigmas or you don't know sigmas. We have all these different cases, and each case has its own formula. So right now, all we did was one case, one formula, and now we're going to do hypothesis testing, one situation. And when we're done with that, then we are going to expand upon it in the subsequent chapters. So my recruits, I got you. We're now going to start chapter 17, which is on hypothesis testing. So here's the idea of hypothesis testing. Essentially, you come into the scenario with an underlying belief about what some parameter is. So you come in with a belief that can't be right, i.e., right? With a belief of what a parameter is. Okay, so you come in, you say, up until now, people have claimed that the average volume in a bottle of Coke is 2 liters. You buy a 2-liter bottle of Coke and you want to believe that it's 2 liters, right? So there's no reason to assume otherwise, right? Up until now, you come in with the belief, okay, 2 liters per bottle. You decide to test that. You have an alternative belief that questions the original. In other words, if I buy a 2-liter bottle of Coke and I pour it all out and I see that it's actually 1.93 liters, I might say, wait a second, wait just 1 second. I think Coke is, they're not giving us what we're paying for. I think really that it's less than 2 liters. So you have the underlying belief that it's 2 liters, and then you come and say, no, I believe it might be something different. This one, the original one, is called the null hypothesis. And the new one is called the alternative hypothesis. The null hypothesis is oftentimes denoted by H sub 0, and the alternative will either be H sub A or H sub 1, depending on the book that you're reading. So you have the null hypothesis, and then you have the alternative hypothesis. And what are you going to do? You will perform some test. I.e., what does that mean? Perform a test, take a sample and measure something, and measure a statistic in the hopes of determining which hypothesis is correct. In other words, you are going to perform a hypothesis test. So you have this underlying belief, you have this new belief, you take a sample, and hopefully your sample will then determine whether or not the null hypothesis or the alternative hypothesis is correct. So how exactly do we do this? Well, essentially, here's the idea. Suppose you believe that a coin is fair. So here's an example. I give you a coin to use to start a football game. The coin toss is the first part of a football game. We will toss the coin to see who gets to kick or receive. So I will give you a coin to use to start a football game. Is the coin fair? Is the coin fair? I don't know. Maybe it is, maybe it isn't. The null hypothesis says that the true proportion of heads should be equal to 0.5. The null hypothesis, claims that the true proportion of heads is 0.5. The alternative hypothesis, the one that we're testing against, is that the true proportion of heads is what? What will be the alternative to the true proportion of heads being 0.5? What is the alternative to that?
Not 0.5.
Not 0.5. It's a perfectly valid alternative, right? You say it's 0.5, I say it's not 0.5. So what do? We decide to test this. We're going to flip the coin 20 times. We're going to flip the coin 20 times. That's the test that we're going to do. We're going to flip the coin 20 times. Now, question. If it came up heads 10 out of those 20 times, would I have any reason to doubt that the coin is fair? Again, if I flip it 20 times and I get 10 heads and 10 head tails, would I have any reason to doubt that the coin is fair? Australia, you say yes. You would doubt it? You would say, I don't think this is fair based upon the results of my experiment.
Yeah, because it's I guess it's happening more than it should be.
Well,
Wouldn't
that's
it be like
right.
50-50?
Well, if I flip it 20 times, isn't 10 heads 50-50?
Oh, you're right.
So I ask again, would you have any reason to doubt the coin's fairness?
No.
No. Have you concluded that the coin is fair?
Yes.
Well, so here's the thing. In stats, we don't conclude anything.
Okay.
In stats, all we have are data which either support one claim or support the other claim. So let me rephrase it. Would 10 heads and 10 tails support the null hypothesis or the alternative hypothesis in this case? Which hypothesis does that data seem to support? It supports the null. But is it really fair? No idea. No idea. But it certainly supports the idea that it's null, that it's fair. Now, if you got 20 heads and no tails, would that support the idea that the null hypothesis is correct or that the alternative is correct? In this case, it would support the fact that the alternative is correct, right? Why? Because even though getting 20 heads is certainly possible with a fair coin, it would be such a rare occurrence that if you have to choose between, oh yeah, that can happen by chance, or it's probably not fair, the more likely outcome would be it's probably not fair. So any results that makes you question, the null hypothesis, question H0. Any result that makes you question H0 is called, and I think we've used this term before, a statistically significant result. Any result that makes you question the null hypothesis is called a statistically significant result. Now, how far away from 10-10 do you have to be before you decide that it's statistically significant? We decided 20-0 is statistically significant. What about 15-5? If you got 15 heads, 5 tails, would you question the null hypothesis in that case? Yes, Flower says. What about 13-7? You think so? What about 12-8? Would you question it? 12-8? Maybe. Well, we gotta conclude something. We gotta conclude something. We either have to say, I believe the null hypothesis is correct, or I believe the alternative is correct. We can't do a maybe. I believe you say it's still uneven, and that's true. But remember, even if it truly is a fair coin, do you really expect to always get 10-10, even if it's fair? No, which means when you get an outcome, you have to ask yourself, could this have reasonably occurred even if the null hypothesis is correct? Or is it such an unlikely event that we are going to reject the null hypothesis in favor of the alternative? So 20-0 could have happened if it's fair, but it's so unlikely we're going to reject the null hypothesis. 12-8, do we reject the null hypothesis? Is that something that we say 12-8, that's such an unlikely situation, let's reject the null hypothesis? Or is that close enough to 10-10 that we say, it could have happened? So luckily, we don't got to do this by hand or on our own. Because some of you might say 12-8 is okay. Some of you might say 13-7 is okay. Luckily, the math will do it for us. So we're going to go through some hypothesis test situations and determine it, whether or not we're going to reject the null hypothesis or whether we're not going to reject the null hypothesis. So just in terms of the language, it's very important to realize you never accept anything. We don't accept the null hypothesis. We don't accept the alternative. We either reject the null hypothesis or we don't reject the null hypothesis. This is kind of like a court case. Anyone here ever either go to court or see a court case or have a situation where the jury will either say we find the defendant guilty or we find the defendant, what's the other option if not guilty? Who's seen Law and Order? It's been out for like 1,000 years. Either we find the defendant guilty or we find the defendant, what do they say? Not guilty. They don't say innocent. They never say innocent. It's either we believe the defendant is guilty or not guilty. In other words, hey, they're here for a reason. They don't go around arresting just random people, but you have not made your case. So we don't have enough evidence to say that they're guilty, so we're going to find them not guilty. We're not going to find them innocent, but rather just not guilty. So here's the same thing. Either we reject the null hypothesis, either we reject H naught, or we don't reject H naught. Never about accepting anything. We either reject the null hypothesis or we do not reject the null hypothesis. Okay, so far so good. Are there any questions on anything so far? Okay, now a term that we're going to use a lot, definition. The p-value of a test is the probability assuming, this is important, assuming H naught is correct. So the p-value of a test is the probability, assuming H naught is correct, that the result actually obtained, or a result even less likely occurred. So the p-value of a test is the probability, assuming H naught is correct, that the result actually obtained or a result even less likely occurred. This is the p-value. If the null hypothesis is truly correct, this is the chance that you would have gotten the result that you actually got. Now, small p-values make us do what? And large p-values make us do what? So again, the p-value of a test is the probability, assuming the null hypothesis is correct, that the result actually obtained or a result even less likely occurred. What would you conclude if you get a small p-value? And what would you conclude if you get a large p-value? No. So the conclusion that we're making here, either we reject the null hypothesis or we do not reject the null hypothesis. One of those situations, and I want a Y also, because otherwise it's 50-50. But one of those situations makes us reject the null hypothesis. And one of those situations makes us not reject the null hypothesis. So we have a large p-value tells us to reject. What is the word next to likely occurred? Less likely occurred. So do we have any other opinions? We have a large implies reject on the board. Do we have any agreement or disagreements? I think I spelled occurred wrong. Is that the problem? Is there 2 R's in occurred? Here, oh. How's that? Is that better? That doesn't look right though. How do you spell occurred? Something looks wrong there. Any English majors? So we had a large reject, we had a small reject. Now we have another small means reject, a large means don't reject. That's 3. How about the rest of you? Without looking it up online, hopefully none of you are doing that. But no one's given me a reason yet. Even if one of you is correct, well, one of you has to be correct because you're, have different answers. How about the rest of you? This is important. It's the whole basis of hypothesis testing right here. Anyone there? We have another small reject. Larger p-values mean larger probability that the event actually occurred. That's correct. A large p-value means a larger chance that the event occurred. That's right. So if there's a larger chance that the event occurred, doesn't it make it reasonable that the null hypothesis is correct? Yeah, if there's an 80% chance that something occurs that the null hypothesis is correct and it happens, you'd be like, oh, okay, well, that's what I expect. So small p-values are when we reject the null hypothesis. If there's a small chance that this outcome occurred and yet it actually happened, then you might start questioning whether the null hypothesis is truly correct. So don't reject the null hypothesis for large p-values, but we do reject the null hypothesis for small p-values. Now the question is, how small is small? As a general rule, in the absence of any other information, we will take small p-values to be anything less than 0.05. So in the absence of a specific number, take as small any p-value less than 0.05. So 0.05 is going to be your benchmark, your fallback, your assumption, unless the problem specifically says use 0.1, use 0.01, use this, use that. Now, also remember that 0.05 is only a 5% chance. So you're basically saying that if p is less than 0.05, if there's less than a 5% chance that it occurred, and yet it occurred, we're going to reject the null hypothesis. 5% is 1 in 20. If I, gave you a gun with 20 chambers, and I, put the bullet in the chamber by random, and said, play Russian roulette or something like that, who here would say 1 in 20, that'll never happen. Yeah, I'll do it. Versus 1 in 20, well, that's not likely, but I'm not going to take the chance. So who here would decide to play, and who here would say, nah, that's too dangerous. Not taking the chance. If it's 1 in 20, right? I think most sensible people will not take the chance for they might never take the chance for any number, like even if it was 1 in a million. But 1 in 20, I think even most sensible people would say this is certainly not worth it. So 0.05 is not really truly that small. So if someone's life depended upon your hypothesis test, or lots of money, or lots of anything, you might decide to take a smaller value as your cutoff, maybe 0.01, maybe even 0.001. Of course, notice that the smaller that your cutoff is, the harder it is to get a smaller value, which means the harder it is to reject the null hypothesis. So if you have a situation where rejecting the null hypothesis is important, and that if you're going to reject it, you want to make sure that you should be rejecting it, you would take a smaller cutoff than 0.05. Does that make sense so far? This idea and theory makes sense? Okay, so what we're going to do now is we're going to do a hypothesis test. And I will show you the, much like the confidence interval that we did, this chapter only does one type of hypothesis test. So example, let's do the following. So it says here, and this is an example from the book. I'm just reading it out here. The National Center for Health Statistics reports that the LDL cholesterol for adults has mean 130. So it reports that the mean is 130 with a standard deviation of 40. The medical director of a large pharmaceutical company looks at the medical records of N equals 72 executives and finds that the mean LDL in the sample is X bar equals 124.86. Okay, so this is a report from out there in the world. It's a report from, what was the example? Report from the National Center for Health Statistics, from the NCHS. And this is a sample from some company. Right, the sample from the company was N equals 72 with a mean of 124.86. And the question is there enough evidence to support the claim that for this company, the mean is less than 130. So again, the National Center for Health Statistics puts out a report that says the mean of some statistic is 130 with a standard deviation of 40. Some company takes their own sample internally of 72 people and gets a mean of 124.86. And the question is there enough evidence to support the claim that for this company, the mean is less than 130? Now, a non-statistician would look at 124.86 and say, well, that's less than 130. We're done. Definitely. Let's move on. Let's not waste our time. But a statistician says, well, wait a second. It's just a sample. Even if the average truly is 130, that doesn't mean everyone's going to be exactly 130. You're going to have some less, some more, some exactly the same. You're going to have people all over the place. So just because my sample is less than 130 is that enough evidence to support the claim that the mean of the entire company is less than 130? So we need to test. Well, so this is the question, piece of all. We gotta test this. We're gonna make a hypothesis test. So what is the null hypothesis in this example? What are we testing against? What is the status quo, the up until now belief without any evidence to the contrary? Would be that the mean of the company is what? 130. If you didn't have any evidence otherwise, there's no reason not to claim that the mean for the company is 130. So the null hypothesis, the incoming hypothesis, the status quo hypothesis, is the mean of the company is 130. What is my alternative in this example? So it's not 130. That is not the alternative here. Read the question carefully. No, okay, 1 second. Wait, I got to correct that right away. The 124.86 came from my sample. Okay, the 124.86 came from my sample. That plays no role in my hypotheses. 1 second, guys, 1 second. The 124.86 that came from my sample, that is purely what I'm going to use to test the hypotheses. The hypotheses themselves are all about what I believe the mean is. I'm not going to believe the mean is 124.86 just because that's what I got. But in this case, some of you are correct. We are testing whether the mean is less than 130. Does that make sense, Cynthia? Okay, so it's not a not equals to here. We're testing whether or not the mean is less than 130. And how are we going to test that claim? Well, we took a sample of 72 people and we got 124.86. So we'll do it in a few ways. The first way we're going to do it is on our calculator. So well, we have a few options here. So option 1, the calculator. I would like you to guess where we're going to go to on the calculator. Where do you think we go to on our calculator? Someone either type or say, where do you think we go to on the calculator? Stat. So it's not second distribution, it is stat. Followed by tests. Followed by it's not an interval, so that eliminates all those down there. Is anyone there? Anyone have the calculator? Which one do you think it is? So it is not 3. 3 is a 2-sample z-test. We don't have 2 samples here. We have 1 sample. So it is 1, just a straight up z-test. 5 is a 1 proportion z-test. This is not proportions, this is means. We have different tests for proportions versus means. This is a z-test. Okay? So let's hit z-test. Now the first thing we'll see, the top line, it gives us a choice. Do we want to use data or do we want to use stats? To use data, we need our actual data points. Do we have our actual data points here? No, so we can't use the data points. So we got to use stats. But in theory, It could be data or stats, depending on what you have. In our case, we're going to use stats. The first one is mu naught. This is what is the null hypothesis belief of what the mean is equal to. So in our case, what is the null hypothesis belief of what the mean is equal to? 130. Okay. The next is sigma equals. What is sigma in this problem? $40. This is assume it's true. If we don't know this, if we don't know sigma, just like with confidence intervals, we'd have a different one to use. With hypothesis test, we'd have a different one to use. But right now we know sigma, it's 40. What is X bar? $124.86. What is N? 72. Next, is this a not equal mu naught or a less than mu naught or a greater than mu naught situation? It's a less than, right? Mu naught less than. So hit less than and then go down and calculate. And what do we get? There's two things that it gives us. I'm going to explain both. It should give you Z equals and it should give you P equals. Let's do the P first since we talked about that. What is the P value here? What does our calculator give us? It gives us about 0.137, which is 13.7%. What does that mean? Let's translate that. What that says is if the null hypothesis is really correct, then there's a 13.7 chance that we got the data that we did. Is a 13.7% chance small enough for us to reject the null hypothesis? No. Now, Cynthia, you said it's the probability that the null hypothesis is correct. Not exactly. It's the probability of getting the result that you did if the null hypothesis is correct. And this is too high of a probability to reject the null hypothesis. So what do we conclude? Don't reject the null hypothesis. We're not claiming the null hypothesis is correct, but your data has not convincingly shown that we should reject it. Your p-value is not small enough. Does that make sense for the p-value approach? Yes, good. The other, what's the lowest probability? Well, in the absence of a specific number, 0.05 is going to be your cutoff. So in this example, they did not give me a specific number. So I'm going to use 0.05. And 13.7% is not less than 5%. So we do not reject the null hypothesis. Yes? Yes, okay. But they do give you a different number here besides P. They also give you Z. And what is the Z that they give you? On your calculator, they should have given you a P and a Z. The Z is negative 1.09. So what does that negative 1.09 mean? It means the following. It means that your data point falls 1.09 standard deviations below the mean. We know that here is 1, so here is 2. So you fell right about there, negative 1.09. That's where you fell. Your data puts you right here at negative 1.09. And what is the probability of getting anything past that? What's the probability that Z will be less than negative 1.09? How do I calculate that? The probability that Z is less than negative 1.09. Anyone, how do I calculate the probability that Z is less than negative 1.09? Count the standard deviations. Well, it's 1.09 standard deviations. That's what Z means, right? Doesn't the Z value give you, or the Z score give you how many standard deviations you are away from the mean? We are 1.09 standard deviations below the mean. And I want to know what is the probability of getting the result that we got or something even less likely. How do I calculate that? You should all know this. We've done it 1,000 times. The Z-score equation. What's the Z-score equation? I'll give you a hint, by the way. Yes, lower upper on calculator. That's correct. What's your lower on the calculator? That's a lower or the upper? Look at my picture. Is negative 1.09 the lower or is negative 1.09 the upper? This is what I'm trying to get here, right? What's the lower? This number on the right or this number on the left? Which of those two numbers is lower? Is everyone here? Even if you don't know, at least acknowledge, at least say something. Be present.
What was your question again?
How do I calculate the probability that Z is less than negative 1.09? Negative 1.09 is the upper. What's the lower? Yes, negative, lots of nines. What's the mean? What's sigma? What will I put in my calculator? Nope, it's 0. This is Z. Z doesn't care about this problem. Z doesn't care about any problem. Z is always a mean of 0 and a sigma of what? 1, always. So on your calculator, go to inverse norm, or not inverse norm, go to norm CDF and calculate for me, please, the probability that Z is less than negative 1.09. What does your calculator give you? Yes, it gives you 13.8%. Now, you might say, hey, those numbers are close, but not the same. Why aren't they the same? Well, they're not the same because we've been rounding a little bit. They really are the same. The p-value is just the probability of getting the result that you got or something even less likely. So the Z and the P are interchangeable. We can use the p-value or we can use a Z and then calculate it the other way. I think the p-value is a little bit faster. So this is how we would do it on the calculator. This is option number 1. We reject the null hypothesis no matter what. Option number 2. We use crunch it. So I'm going to stop sharing here. And I will start sharing here. And we will go, for this example, we will go to, is there a crunch it on this? Well, we'll go to crunch it. I'll have to not use this data here, so I'm just going to delete this column. Okay, so where do you think we go on crunch it to do a hypothesis test? Who wants to venture a guess as to where we go on crunch it? What should I go to? File, edit, insert, filtering, statistics, graphics, or distribution calculator? Someone said statistics. Okay, let's go to statistics. Which one under statistics should I go to? So someone said distribution. Oh, you're going back to the beginning, distribution. So which one of these should it be if it's not statistics? Stats Z. If I go to stats Z, is it 1 sample or 2 samples? Okay. So here I am. What do I put in? Do I have data or am I going to summarize my data? Which will it be for this example? Do I have data or will I summarize my data? Summarized. What should I put in for N? Okay, 72. What should I put in for the sample mean? 124.86. What should I put in for the standard deviation? $40. Is it a hypothesis test or a confidence interval? Hypothesis test. What should I put under the mean under the null hypothesis? $130. Is it a two-sided, a less than, or a greater than alternative? Less than. Calculate. What's my p-value? Is that the same thing we had before? Within the rounding error? Within rounding, is that the same thing? Yes, it is. Notice it gives us a z statistic, negative 1.09, the p-value, and then it writes out the null hypothesis that the population mean is equal to 130. The alternative, that it's less than 130. Wasn't crunch it easy? Wasn't bad, right? I personally like the calculator because it's a lot easier to carry around the calculator than it is to carry around the computer that has crunch it on it, but they both work. Of course, option 3. So let me unshare this now. Option 3. Whoops. Is to do it by hand. We should know how to do it by hand as well. So option 3 is to do it via the formula. So the way we do it via the formula is, oh, what are those little bugs called that just don't seem to die? You know, the little ones. They're back. Anyways. So what we're gonna do, fruit flies, that's what they are. They're the worst. They're back. They're back. I hate them so much. Okay, anyways. So here's what we're gonna do. Let's recall what our data was. Okay. Our data was the null hypothesis. I'm just gonna rewrite it, was that mu is equal to 130. The alternative is that mu is less than 130. We decided to take a sample of 7 and sigma is 40. We take a sample of 72 and get an X bar of, what was it, 124.86, I think it was. All right, was that it? Okay, and from this, we would like to determine whether or not we're going to reject or not reject the null hypothesis. Doesn't really look like a lot of information, but it's all we need. So the way we do it by hand is we compute the z-score. Now remember the formula for z-score. Z-score was data minus mean divided by the standard deviation. That's a general formula for calculating the z-score. What's our data? 124.86. What's the mean? Remember, we always assume the null hypothesis is correct, because the whole question is, if the null hypothesis is correct, does this outcome make sense? So we are assuming that the mean is 136. What is the standard deviation? Spoiler alert, it's not 40. Oh, certainly not 1. This is not z. Remember, we're
Is it the negative 1 point?
no. Negative 1.09 was something we calculated. So we can't use that because that was what we got from a different approach. This is option 3. It's like we didn't do option 1 or option 2. And Luis is not 1. 1 is the deviation for a z, but we don't have z yet. We're getting to a z. We're computing the z-score. So we're not yet at a z distribution. It has to be the standard deviation for our problem. Now people were saying 40, but it's not 40. Because remember what we did last time or possibly the time before. Actually, I alluded to it today. Right here. What do we do to the sigma when we take a sample of size n? We don't just write sigma, but rather what do we write? I just ovaled it. No, I just ovaled it. We don't do sigma. What do we write instead of sigma? We have to somehow take into account that we have a sample. Look, I circled it. Now, it's not, there's nothing in that circle, it's SX. I'm not sure where that's coming from. X bar minus Z star sigma over what? We all see what I'm looking at? Over what? Over root n, not over, oh, I hit the wrong button. Not over root n, sorry, not over n, over root n. Over the square root of the sample size. The standard deviation of a sample is the original standard deviation divided by the square root of the sample size. This is a, remember, we did this for sure. We had a day where we talked about the population distribution versus the sample distribution. And we said if the population mean is mu, the sample mean is mu, and if the population deviation is sigma, the sample distribution is sigma over the square root of n. We definitely did that. Does anyone recall this vaguely? Just so I know I'm not being completely delusional. But when we have a sample, we don't just do sigma, we do sigma over the square root of n. So when I do 124.86 minus 130 and divide that by 40 divided by the square root of 72. What do you think I get? What do you think I get? 97. Woo, buddy. Where did that come from? The top is negative, so I'm not sure. I'm not sure how you get a positive number in the first place. 124.86 minus 130 is a negative number. I think you might have. So what is it? Negative 1.09. This is the same Z that the calculator gave us. At that point, I just do this calculation here, which we did before, to get the p-value if I am so inclined. 3 methods. Method number 1 is a calculator directly, just put your data in and get it. Method number 2 is crunch it. And number 3 is doing it by hand. Let's do another one, shall we? Let's see if I can find one here. Okay, so here's another example. Before we do another example, are there questions on this example? Okay, so let's do another example. We have the following problem. It says, a random number generator is supposed to produce random numbers uniformly distributed on the interval from 0 to 1. That is what it's supposed to do. If this is true, the numbers come from a population where a mean is going to be 0.5 and whose sigma is 0.2887. So we take a sample and we ask it to generate 100 random numbers, and it gives us an X bar of 0.5635. And sigma is correct. We're assuming that sigma is correct here. So if we are desiring to test whether or not this random number generator is working properly, okay, then what would the null hypothesis be? And what would the alternative hypothesis be? So we're assuming the mean is 0.5. That's what the null hypothesis is, because that's what the belief is up until now. So why not? And what would the alternative be? If it's not working properly, then what would you be able to tell me about the mean? That is not equal to 0.5. Correct. This is not a less than or greater than situation. This is a not equal to situation. If it's not working properly, that means it's either less than or greater than. Either one would qualify as not being 0.5. Sometimes from the context of the problem, you have to ask yourself, is it one-sided or is it two-sided? It's not always going to be given that way. So the question is, at 5% significance, what do we do? So part A, at 5% significance. In other words, if the cutoff is 5%, what do we do? And B, at 1% significance, what do we do? So the question here, a two-parter, what do we do at 5% cutoff? And what do we do at a 1% cutoff? So which method should we use to do this? Calculator, crunch it, or by hand? Calculator, okay. So where am I gonna go with my calculator? Stat, okay, next. Stat, test, Z test, that was quick, okay. Am I gonna put in data or am I gonna put in stats? Okay, what should we put as our mu naught? .5. What should we put in there as a sigma? .2887. How about our X bar? .5635. How about our N? 100. Is it not equal to, less than, or greater than? Okay, let's calculate. What is our p-value? Actually, the p-value is for A or B, it's just a result. So what is our p-value here? 0.0278. So A, at 5% significance, what do we do? We reject the null hypothesis. Why? Because we are smaller than our cutoff. Reject H naught. And at 1% significance, what do? We do not reject null hypothesis. The smaller the significance level, the harder it is to reject. You got to be that much smaller to reject it. Does that make sense? Now, let's take a look at the other approach, which is the z-value approach. So they told me that P is 0.0278, but they also gave me Z, 2.1995. So let's take a look at that approach. Where is 2.1995 on my graph, on my distribution? Where would that be? A Z value of 2.1995. Where's that located? On the right side. So here's a Z value of 0. Here's a Z value of 1. Here's a Z value of 2. So 2.1995 would be over right here somewhere. Maybe a little further to the right, about there somewhere. So does that mean that this is the area that corresponds to this problem? The answer is no. And you might say, whoa, wait a second. When I went to this problem here, I found my Z, which was negative 1.09, and I said anything past it, anything less than it, because wasn't that the problem? Z less than negative 1.09. And I calculated the probability, 13.8%, p-value, 13.8%. Hey, it's the same thing. So here, why is it not the right side? So the answer is because this is not a greater than test. This is a not equal to test. Right? Not equal to. Yes? That means there's two ways that I would conclude that the mean is not really 0.5. Getting numbers far to the right like we did, or getting numbers where? Far to the left. So what we do for a two-sided test is we actually double the area. Because for a two-sided test, there's actually two ways to reject, far left or far right. So when I calculate the probability of being past 2.195, let's calculate that. What's the probability that Z is greater than 2.1995? How would I calculate this? How would I calculate on my calculator the probability that Z is greater than 2.1995? How would I calculate that on my calculator? Normal CDF, good. Second distribution, normal CDF, good. And what would I put in? Well, go ahead, you gotta give me everything. It's like 4 things I gotta put in or something like that. Lower is what there, Cynthia? We're just doing this side here on the right. So what should the lower be?
Would it, the lower on the right side, you mean, would be 99999?
No, that's the upper, that's the far right. Remember, lower is the left side, upper is the right side.
Oh, okay, I'm sorry, yeah, so the lower would be 2.1995,
And what
And
was
then
the upper?
9999,
Okay, with what mean?
0,
With what sigma?
1.
Okay, what does it give me?
Hold on, I still have to do it. I was just going off what I remember.
I understand.
2. 0.41, 0.41.
What did you put in exactly? Because that doesn't make sense.
Oh, hold on, I think I did lower.
Tell me what you put in.
Okay, I did. Oh, I'm sorry, I put 0.2199 when it's 2.1995.
Rookie mistake.
Okay, and then, okay, so I got 0.014.
Okay, or 0.0139.
Okay,
Now, in this case here, when we did it on a calculator, we got exactly the same number as the p-value. The probability of being less than negative 1.09 was our p-value. But here, notice that we did not get our p-value. Why not? No, not because of that. Remember, Diana, we don't know whether it's correct until we finish our calculations. So we can't conclude something because it's not correct or because it is correct until we determine that it is correct or not correct. So the answer is, as Jason said, this is a not equals case. The total p-value needs to take into account both sides, not just one side. If we take our number 0.0139 that we just got and multiply it by 2, to take into account the other side, what do we get? If we do 0.0139 and multiply it by 2, we get 0.0278, which is the p-value. So for a two-sided test, the side that you landed on, you got to take that probability and multiply it by 2 because the p-value incorporates both sides. But at the end of the day, it's the p-value that determines whether or not we're going to reject or not reject the null hypothesis. If the p-value is smaller than the level of significance for the test, which is usually 5%, but might be more or less depending on the problem, then we reject the null hypothesis in favor of the alternative. If the p-value is not less than 5%, or if the p-value is not less than the level of significance, then we do not reject the null hypothesis in favor of the alternative. But it's always about, do we reject the null hypothesis or do we not reject the null hypothesis? That is the question. So does this make sense, what we did today? Okay, at this point, we have learned confidence intervals and hypothesis testing. Over the next bunch of chapters, we're just going to be doing lots of different examples. Here, in this case, you do this one. In this case, you do this one. In this case, you do this one, and so on. But in theory, we're done. In theory, everything about confidence intervals and hypothesis testing that we're going to learn, we have learned. In theory, it's all over. Okay? So, any questions on anything that we've done so far? All right, well, in that case, this is what I wanted to cover for today. So I'm going to stop recording. And, oh, question, just go ahead.
Just real quickly, do you mind explaining why at 5% significance, why we reject it, the null hypothesis?
Because your p-value is smaller than the level of significance. Your p-value here is 0.0278, right?
Mm-hmm.
Your significance level is 5%, which is 0.05. 0.0278 is less than 0.05.
Okay, so when it's less, than, we reject it.
Yes, when it's less, when your p-value is smaller than the level of significance, we reject the null hypothesis. If it is not smaller than the level of significance, then we do not reject the null hypothesis.
Got it. Okay, thank you.
Okay.
Yes. Thank you.
All right. Any other questions? In that case, have a good weekend, everyone. Get all the studying done for the mini quiz that's due by Tuesday, and I'll see you on Tuesday.